Every year, plant diseases quietly cost the global agriculture sector hundreds of billions of dollars, not because we cannot detect them, but because doing it precisely requires data that is incredibly hard to collect. Imagine trying to outline every tiny disease spot on thousands of leaves by hand. That is what pixel level segmentation demands. And it hits a fundamental wall. Labeled data is rare, expensive, and inconsistent. So the question becomes, what if a model could understand how a plant works before anyone labels a single pixel? And this reason became how I just built my own AI architecture to contribute to the solution of this problem. I know, that sounds crazy, but it is actually true. Well, you might think, how did a normal high school student, Jayden Lee, have built his own AI architecture? Well, I introduced to you my project, LeapSeg, leveraging IJPA, VIT, UNet, and YOLO to gain efficiency in leaf disease segmentation. I will break down my project into 5 clear steps, starting with the problem in the previous architecture and to the result of my architecture. Modern AI models are incredibly good at finding patterns in images. Models like UNet can look at the leaf and precisely outline where disease is present. But there is a catch. To learn this, the model first needs thousands of examples, where every tiny disease spot has been carefully traced by human. And not just any human. Often it requires experts who understand the plant diseases thoroughly. But now, imagine doing that for thousands or even millions of leaves. That's the bottleneck right there. The places where we need automated disease detection, farms, remote regions, and developing areas are the exact places where collecting that kind of detailed data is hardest. So the real challenge isn't whether AI can detect plant disease, it's whether it can do it when almost no labeled data exists. Now, recent advances in AI offer a different way to approach this problem. Instead of relying on a labeled data, a new class of methods called self-supervised learning learn directly from raw images. One example is IJPA, short for Image Joint Embedding Predictive Architecture. At a high level, it works very differently from traditional approaches. Instead of asking a model to fill in missing pixels, iJPA asks the model to understand what should be there. It looks at part of an image and learns to predict the meaning of the missing region, not just its exact appearance. This difference is important. If a model focuses only on reconstructing pixels, it tends to memorize textures and surface details. But if it learns to predict representations, it starts to understand structure, how different parts of an AI relate to each other. In other words, it begins to form an internal understanding of the scene. This idea connects to something larger in AI, what researchers call a world model. Instead of just recognizing patterns, the model builds a mental picture of how things are organized and how they behave. For plants, that could mean learning the shape of leaves, the structure of veins, and how healthy tissues differ from damaged areas, all before ever seeing the labeled image of disease. Therefore, my project, LeapSeg, is built around this simple idea. Teach the model to understand plants first, then teach it to find disease. The system works in 2 stages. Stage 1 is pre-training. Here, we use a vision transformer or VIT, a type of model that looks at an image in small patches and learn how those parts relate to each other. Instead of focusing on one local region at a time, it captures a bigger picture, shape, structure, and spatial relationships. We train this model using iJPA on a large set of unlabeled plant images. No annotations, no labels, just raw data. Over time, the model learns what plants generally look like, their leaf shapes, vein patterns, and natural structure. Stage 2 is fine-tuning. We take this pre-trained VIT encoder and connect it into a UNet-style decoder, which is designed to produce detailed pixel-level outputs. The encoder provides rich features, while the decoder refines them into precise segmentation maps. The key idea is straightforward. If the model already understands plant structure, it should need far fewer labeled images to identify disease. In this way, the model does most of the hard learning upfront. Fine-tuning becomes less about learning from scratch and more about sharpening what it already knows. We evaluated LeapSeg under a label efficiency setting by varying the amount of labeled training data from 1% to 100%. Three models were compared: a baseline unit, a supervised VIT unit, and the proposed IJPA VIT unit. Performance was measured using die-score and intersection over union, which also stands for IOU, so the comparison captured both overall overlap and the quality of lesion boundaries. The central question was straightforward: when labeled data are limited, does self-supervised pre-training actually help segmentation performance? The results were encouraging. On the held-out test set, the IJPA VIT unit achieved the strongest overall segmentation performance, reaching a die score of 0.7 and an intersection over unit score of 0.74 with just under 20 minutes of training time. More importantly, it performed better when labels were scarce. At the lowest label setting, it outperformed the supervised VIT unit by roughly 4 percentage points in dice with a similar gain in intersection over union. As more label data became available, that gap became smaller, which is expected. But in the low-level region, where agricultural systems often struggle most, self-supervised pre-training gave the model a clear advantage. Qualitatively, it also produced finer lesion boundaries and fewer false detections in healthy regions. So the takeaway is not that supervision no longer matters. It is that self-supervised pre-training makes limited supervision far more effective. Now, research performance on benchmark is necessary but not sufficient. To evaluate LeapSeg under deployment conditions, we integrated into mobile agricultural rover system. The pipeline works in two stages. First, a YOLO-based detector scans the camera feed in real time, identifying plant regions and isolating regions of interest, handling the fast, coarse-grained localization problem. Then, DeepSeg operates on each crop region, performing fine-grained disease segmentation at the lesion level. This is a deliberate division of labor: YOLO for speed and coverage, DeepSeg for precision and interpretability. Therefore, DeepSeg demonstrates that the path to scalable agricultural AI does not require more labels. It requires learning more from the data we already have. And by combining principled self-supervised pre-training with real-world deployment, we move closer to perception systems that are robust, efficient, and ready for the environments that need them most.